we're going to talk about ZFS. Well, so this is the second video in a little video series about building a disk array, in particular sort of the largest storage array, not really meant for tons of random I/O, more for things like storing music and videos you're going to stream from, backup, stuff like that. And the first video we talked about SAS and SATA and about the array configurations and how you can hook up hard drives to a computer. And in this video, we're actually going to go try this out. We're going to build a bunch of different pools of different types and see how they perform in a couple different ways. And so I thought before we jump into that, just real quickly, so our setup is we have this JBOD, and the JBOD has in it 16 disks. So it's got 16 disks in here, and they're 14 terabyte drives, little Western Digital SATA drives. And this chassis has coming out of it a SAS 8088 connector. So going to a cable and then over into a server. And our little server is a little dual Xeon that has an HBA in it on a little PCI or Express bus. And that cable goes into there. And of course, this cable has 4 lanes of 6 gigabit per second, either SATA or SAS. And the drives over here, these are all SATA drives. And so that's what we're using to sort of build the array. And we're going to try a bunch of different configurations. So 16 drives. So we're going to try just putting all 16 drives in one gigantic RAID0, just sort of a span of RAID0. So they're all individual vdevs, which is, of course, the best for performance, but there's no redundancy. We're then going to move over and do mirror sets, where every drive is paired with a second drive. So there are little mirror sets of 2 drives. And of course, we have 16 disks. So there'll be 8 of these mirror sets. So we'll have a total of 8 vdevs, each with 2 disks in it. And that's a good mirror, a very common mirror configuration. And then we're going to do RAIDZ1. We're going to do that in 2 vdevs, each one with 8 disks. So 2 vdevs of 8 disks. And then we're going to do RAIDZ2, the same thing. We're going to do 2 vdevs of 8 disks each. And then we'll do RAIDZ3, same thing. So 2 vdevs of 8 disks each. And of course, between the 1, 2, and 3, in the 1, you lose basically 1 disk worth of space in each of the 2 vdevs. And in RAIDZ2, you lose 2 disks worth of space in each of the vdev. And RAIDZ3, you lose 3 disks worth of space in each of the vdevs. So obviously in RAIDZ3, you're going to get the least amount of space versus RAIDZ2 versus RAIDZ1. And then we're actually going to then try another quick trick, as we're going to take RAIDZ2, and we're going to instead do 3 vdevs of 5 disks each. And so that will be very similar in size to the RAIDZ3, and we're going to have 1 extra disk, by the way, so we're going to make that a hot spare. So this is RAIDZ2, but with more vdevs. And so we'll be kind of get an idea of the difference in performance between having 3 vdevs versus having 2 vdevs, and just try to get an idea of which one of these is sort of the best for our particular use case. I think in the big picture, one of the things to understand is that over here in the world of mirror drives, you have 8 vdevs, and each vdev is composed of 2 disks. And in this world, if you lose a disk, so disk crashes and you get an email saying, hey, we lost a disk. So at that point, you have 15 disks left. And 14 of those 15 disks, if you lose, won't hurt you. But one of the disks, if it's the other one in that RAID pair, if you lose that, then you lose the array. So you have like a 1 in 15 chance that the next failure is going to kill the array. And that's sort of well known in the mirror world. And generally, if you had a setup like this with mirrored for high performance, you'd probably have a hot spare drive sitting in the chassis as well. That way, if you lose a drive, the hot spare will come in and start resilvering as fast as possible. So there's not a lot of delay there, because it is somewhat higher risk that you could lose 2 disks. And if you lose the right 2 disks, you could lose the whole thing. With RAIDZ1, of course, you can lose a disk, and now this particular vdev is now in a faulted state, and you haven't lost any data. And you're going to have 7 disks here and 8 disks here, so you got 15 disks left. And in this case, though, you have 8 disks over here. You can lose one of those and nothing bad happens. But if you lose any one of these 7, so 7 out of the 15 disks, if you lose one of those, then this vdev's gone, and then the whole array is basically lost. So, RAIDZ1 carries with it some risks past one disk failing. And if you had a RAIDZ1 like this, yeah, you'd probably want to have a hot spare sitting here ready to jump in if a disk dies. Of course, it has to resilver. And in general, RAIDZ1 with big disks is kind of a no-no for that reason. Because the resilver time is so long, it might take it 2 days to resilver. It just increases the probability of another bad drive. And also keep in mind that hot spares are sitting here waiting, but they aren't getting used, which is potentially dangerous because you won't know that it's a drive that's bad until you try to use it. Obviously, with RAIDZ2, you have the nice thing that if you lose a drive, right, and you now have 7 drives here and 8 drives here, you have 15 drives, you can lose any of those 15, even if it was a second one here, and you still have a fully functional array that hasn't lost data. And so RAIDZ2 offers a significant advantage because you can lose any of the 2 disks in the array and still be okay. And then the next 3rd disk you lost, you have 6 here and 8 here, so you have a greater than 50% chance of losing a disk that's not going to hurt the array. So RAIDZ2 offers that significant protection. And so really RAIDZ2 is kind of the benchmark one you're going to see used for this kind of storage array. Of course, RAIDZ3 means you have 3 replicants, so you could lose one, and then you could lose another one, and you still have a 3rd replicant copy effectively of data in this array. And you might use RAIDZ3 if it's something that you really, really don't want to have to restore ever from a backup. And maybe you think you can't get to the array very fast. Maybe you do have a hot spare sitting here, but you only have one. And so having that extra resiliency of a 3rd layer of parity here gives you some protection. You just lose a little bit of storage space, and you'll lose a tiny bit of write performance because now you're writing a little more data for all the write transactions. And so it's something to keep aware of when we're kind of building these arrays, that in general, you'll find RAIDZ1 is not going to be used much for this. And RAIDZ2 offers kind of a really good compromise between the performance you can get for it and the reliability, particularly if you can get to the machine at some point and replace a drive. So that's sort of the concept. So let's jump into our actual machine and take a look at the configuration of the machine and start creating arrays. Let's start up this array. So we're logged into the server that has the disks. And let's take a look here. Let's do LSCPU and grep for the model. Let's see what this is. Okay, so this server is dual Xeon E5 2637V2s, which is really old, probably 12-year-old TPUs. They are the faster variant of that 2600 series. I think it's 4 cores. But for a file server, this will probably work okay. If you look at the memory, this machine has 256 gigabytes of RAM, and that will be the most helpful thing because it can use that for the disk cache. By default, I think the ZFS, we can look at arc summary, it will use half, let's dash P1. I think it'll by default use 128 gigabytes, so half the system memory as the max that it will use. If this server is going to be just a file server, then I'm probably going to end up upping that a little bit, maybe giving it 75% of the memory. It's not super critical, but it's worthwhile to have the memory used a little more for cache. And then if we look at, if we do LSPCI and we grep for SAS, we can see there are 2 SAS controls on this box. The second one here is the onboard control on the motherboard that goes to the drives at the front of the case. And they're both 2308s, which is a SAS2, so 6 gig SAS controller. And I believe if we do LSPCI, I think verbose and put it through more, and we search for SAS. This is that first SAS controller, and we can see that it is, here we are, link speed, yeah. So it's an 8 gig transfer per second with 8, which means PCI Express version 3. And so 8 channels at 8 gig transfers per second. And keep in mind that this card has 2 4-port SAS ports on it, so that matches pretty well. So there is enough PCI bandwidth in the card connection to the computer for the amount of bandwidth available in the 2 SAS ports. So that's kind of a good thing to keep in mind. If for some reason it was an older card that was the 5 gig transfer per second, it may be insufficient bandwidth to really max it out, but this has sufficient bandwidth. There was another utility we can use called SAS2 Flash, which is a utility used to flash LSI cards, but I think I have to run it. I think I have it in this directory. I think if you do -list all, it'll show all the cards. Yeah, this shows the cards, the onboard one's the second one, the 0 is the first one. And it shows what version of the firmware. This has 16 and 17, which is an older firmware. I think version 20 is the latest. So probably worthwhile for me to upgrade those at some point. Sometimes the firmware upgrades fix compatibility with some drives. I think that on some of these, the BIOS upgrade will also change support for more disks. I remember one of them, if you had more than like 128 drives, you had a problem. So not something we're going to have today, but something to be aware of. And you also can do, I think SAS2 Flash supports -O means do advanced commands. And there's a test, I think it's ls all, and you can tell it which card to do. And that will tell you what the actual negotiated speed for the physical interfaces are. And so one of them plugged in, this is the control 0 is the one that's connected to the drive JBOD. And sure enough, they're all 6 gig links. So you can do this to verify that you're getting 6 gig connections to the JBOD. If it was a 12 gig JBOD and a 12 gig card, you can use not SAS2, but SAS3 Flash, same thing to determine, to make sure that you're negotiating 12 gigs. So it's just kind of good to verify that we're negotiating 6 gigs on all 4 channels to our JBOD. So we're kind of set up there properly. So next in mind is, let's take a look at the disk. If you do ls block, it'll show you all the block devices. But if you do ls block -D, it's a little more readable because it'll get rid of all of the partitions. And so you can see we have these 12.7 terabyte, which there are 14 terabyte disks. And you can see we have 16 of these 14 terabyte disks, along with the boot disk, which was an SSD, and then another SSD we can use if we want to use it for a cache drive later. So very simple. So the goal is to take these 16 14 terabyte drives and make an array out of them in ZFS and then kind of test the performance of it. And so we're going to start. Let's start, first of all, let's just look at one of these disks. If we do, take a look at the first disk, and we'll output to dev null. We'll do a block size of 1 meg and a count of, say, 1280. So the goal here is we can look at, we'll do iflag, which just makes sure that we don't get any caching there. Let's just read in from one of the disks and just see how fast this hard drive is. They're all the same hard drive type, so we'll just get a rough idea. And sure enough, we get 276 megabytes a second, which is about what I'd expect. Most of these spinning hard drives in the sort of 12, 14, 16, 18 terabyte range are going to read anywhere between 250 and 300 megabytes a second. So this is just what you'd expect. So a single drive maxes out at about 276 megabytes per second. So that kind of gives you an idea of what the capacity of one drive is. And of course, we have 16 of them. But if, and I made a little script here, if we look at the scripter 8 direct, it just does DD from the first 8 disks all at the same time. So if I run this, it's going to read from all the first 8 disks all at the same time. And we'll see this ends up being slightly slower, not a lot slower. They're in the 260s, so just slightly slower than the peak rate we got with just one disk. And this is actually not a function of running entirely out of the peak SAS channel bandwidth, but there's a little bit of latency in SAS to SATA, and the SATA itself is half duplex. So there's a little bit more latency added in those commands. And so doing a bunch of reads in parallel, that latency adds up a little bit. So we're getting a little bit less than full performance, but still pretty good. We're getting most of the performance of 8 drives. But I also have another script here to do the same thing, just 16 disks of DD. That's all it's doing. And if we run that, that's going to read from 16 drives at the same time over this 4 SAS channel connection. And this will almost certainly be slower per disk. We'll see how it goes there. Yeah, 135. So about half speed. And so the takeaway here is that, and I mentioned this in the previous video, that if you have a JBOD that has 16 disks or 24 disks or 32 disks or 36 disks, and it has a single SAS 4-channel interface, that 4-channel SAS interface, 4-channel 6 gig SAS interface with reasonably performant hard drives is really good for maybe 8 to 12 disks before you're oversubscribed. And sure enough, at 16, we're oversubscribed by quite a bit, almost 50%. And so it's a good indication of like what the max speed is. So this kind of gives us this ballpark number that at most we're going to get 135 megabytes per drive if they're all going at the same time. And if you look at the SAS2 interface for channels, you can get around 2 gigabytes a second, between 2 and 2.2 gigabytes a second, maybe a tad more if everything's perfectly aligned. The theoretical will be about 2.4 gigabytes a second, and that kind of gives you an idea of what the upper ranges of what it might look like. And so what we're going to do first is that we have all the disks here, and a couple of things to keep in mind. If you do ls block, it gives you some information. But if you add -o, you can give it like some other parameters you want it to show, which we'll have it show the path, the model. Let's do the serial number, the WWN number, and then each controller will tell you which controller it's on. And so if you do that, it will give you a list with those parameters. And this is really important to do when you're building an array, because every disk has a WWN number, which is a unique number for that particular disk. And if you pull the disk out of the array and put it back in the array somewhere else, it could be on a different controller, it could be a SATA disk, and you move it to a local SATA interface on the motherboard, doesn't make a difference. The WWN number stays the same. So the WWN is a unique identifier for the disk. And so when you're building an array, you should use the WWN numbers as a way to identify the disks when you're making the array. And what I mean by that is that if you, let's do this here, if you look in dev disk by ID, and you look for WWN, and then we could take one of these numbers here. Let's take this first one here, and let's type that in there. If you do this, you'll see that, of course, that maps to dev SDA. And so if you use this string when you're making your zpool, instead of using dev SDA, then you're making it using the ID of the disk. So you want to do that so that the pool is made with the IDs of the disks regardless of the particular boot order. Because sometimes if you reboot this machine and for some reason the SAS controller or the SAS array, maybe you power cycled it a little bit later and it's coming up slower, it's possible that other disks will come up before these and get assigned earlier. Therefore, they'll take over these slots. And so in general, you want to avoid using things like dev SDA for any scripts or anything. Instead, use the WWN ID to find the actual disk. And that way, if it moves around, you'll still find it. So we'll do that when we create our array. We'll use the WWN numbers to create the array. And so we're going to start off in our little array building exercise. And I made a little script here, create span. So this is a little shell script that it takes all the disk names. So I'm using the WWN ID disk names. And this is going to create a zpool that is just a span of all the disks. So effectively RAIDZ1 being striped across all the drives. So there's no redundancy. And you wouldn't normally ever use an array like this because, well, if a single disk fails, you'll lose the whole thing. Occasionally you might use one of these for something that's super high performance. That's a very temporary thing, but even that, there are probably other ways to do that. But there is a reason to do this. And I encourage you, if you're going to build an array, once you get all the hardware set up, do this first and test it out. And the reason is because this represents the high bar of performance for what your particular hardware is going to be able to do. Because this is striping every single disk with no redundancy. And so it's worthwhile to just do some testing with this configuration, even though you're not going to ever use it for real, because it lets you know what the high bar is. So then when you start making other changes and you're trying different arrays, you have a good understanding of how much you're losing from what could be the very best performance. And so we're going to do that. So I'm going to run this script here, and it's going to create this zpool with all the disks being striped. And there are 16 disks, and they're each 14 terabyte disks. And so here we are. So the total disks is 204 terabytes, and sure enough, this array ends up being 204 terabytes in size. There's no redundancy, so there's no loss anywhere. And so now we have an array set up, and it is shared for testing. So we're going to do a little bit of testing from Windows. And so I'm going to pop over here. This is a Windows box that's on the same network. And it actually has two network connections that are of interest, Ethernet 2 and 3 here. And these are both 10 gig network connections. So one is for the my sort of storage network, and the other one's a backup network. But one interesting thing about SMB3, and I'm going to go ahead and fire this up here. We're on the Z drive. I'll let that run. But one interesting thing about SMB3, which is true for Windows and also newer versions on Linux, is that it will look and see if you have alternate network connections that are of equal speed. And if you do, it will use them. And in this case, you can see it's using both networks, even though when I mounted this drive, and I can show you here, I only used the one IP address, but it will talk to the server side and say, hey, are you on any other networks? And if you are, and we're on the same network, let's use that connection. And so you can see it's using both connections. And these are both 10 gig connections. So you can see that it's basically almost fully taking both 10 gig connections. So we're getting 20 gig of bandwidth between this Windows box and our file server. And over here, you can see that sure enough, we're reading and we're getting 2.3 gigabytes per second, which is pretty good. That's about as much as we're ever going to get because we're limited by this 20 gig network connection. And so let's let this run. It's going to do 2 different sequential read tests and then 2 different random read tests. And then it'll fault over and do the sequential write tests, both one with, I think, 4 threads, one with 8 threads. And so we'll let this run and then we'll take a look at the results. All right, so this is just finishing up here and it's done both the sequential and the random operations. It's finishing up the last one right now. And there are a couple interesting things to note here. So first is that, we're getting 2.3 gigabytes a second of read and almost 1.8 gigabytes a second of write. And those are pretty good numbers. And they, of course, sound suspiciously close to the peak bandwidth of our network connection. And on the random IO, I think this first one here, the thread 16, 140 megabytes a second for the random IO on read and 70 something on write. What's interesting about these numbers, and this is true about this tool and about this configuration, is that Crystal Disk Mark, you tell it the size of the file you want to do, and it will create a file and it writes it first, and then it uses it for the read benchmarks, either sequential or random. And then it uses that same file writing into the file, either randomly or sequentially, to measure that performance. And that means a very important thing. It means that when you first write that file, of course, on the ZFS side, that's going to get pulled into or written into the ARC cache, as well as put into transaction groups, meaning it'll be in the read cache. And that's designed on purpose because if you write something, they expect you might be reading it back again. And so let's have it in the cache. And so what these numbers tell you is nothing to do with the performance of the array. This tells you how fast your cache is, and how fast your server is, and how fast the network connection is between this box and the server. So this peak rate here of 2.3 gigabytes per second is almost entirely coming from cache. And in fact, if we were to run this again, and I'll do it in a minute here, you'll see that there'll be no read operations on the Z pool because it's all coming out of cache. And so in this configuration, this test is not particularly helpful. If we were to switch over and make it, instead of this RAID0 stripe, if we had done a mirror or a RAIDZ1, the sequential numbers wouldn't be different really much at all. A little bit different, but not a huge difference. The random numbers will change a little bit, but mostly on the write side than the read side. And so that's because, of course, of the caching. But there's a second variable really important here, which is that this is over SMB. And SMB by default does asynchronous file writing, meaning when it talks to the SMB client, the SMB client makes all of the writes asynchronous. And that means a very particular thing. It means that when the SMB side, so this is the application here, says, here, write this block, it'll make its way across the network to the SMB server. The SMB server will hand it off to ZFS and say, write this. And ZFS will say, oh, this is async. And it'll say, thanks. And it's done. And that transaction will finish and it'll go back through the network, back over to here and say, okay, block done. What do I do next? Even though that block hasn't actually been written to disk yet. And internal to ZFS, it takes transactions that come in that are write transactions and it saves them up a little bit into these transaction groups and then executes those groups, which is really cool because it enables it to do really efficient striping across the disks of these write groups and to organize them such that sequential writes across the disks are in the correct order. And it has some internal timers. I think the default is something like 5 seconds, I think, where it won't hold the data in memory for more than about 5 seconds before it'll write it out. But the problem with async is that it effectively is a tremendous amount of write caching from the point of view of the application. And so if you have synchronous or asynchronous operations, you're really not getting a super good job of judging how fast the array itself can write. And that's the default with SMB. But if you want, so we can see these numbers here. And so we see the 2.3 and the 140 and the 70. So if we go back over to the server, so we can do ZFS set, and there are two variables. The first one's called sync. And we can set it to always. And if you do that, and the array is called test, then now it'll do synchronous writes no matter what the other side says, even if it's SMB who is normally async, it'll force them to be sync. And we can also do set primary cache, and we can set this to metadata instead of all. And so this will effectively turn off the use of the ARC cache for reading. So if we do these two things, and we go back over here, and we run these tests again, and we'll run them again here and let them go, we will get somewhat different numbers because now the actual disk IO is going to be for real. In fact, if we go back over to the primary array here, we can do zpool IO stat and kind of see what's happening in the array. And we'll see that it's writing, it's writing at about 60 megabytes a second, which is very slow. And that is because we have turned on that synchronous writing. And so now this client, even though it's over SMB, is doing everything synchronously. So we're going to let this run for a minute. It'll take it a couple minutes to run to complete all the tests. And this will give us sort of what you might describe as the other end of the bar. So the all caching, all asynchronous gives you the very high end, like the fastest your array is going to be, basically 100% hit rate on the cache. So it's really, really, really a good high bar. Now we're going to see sort of the low bar, which is that assuming we never get a cache hit and all the writes are synchronous, what does the array look like? And this will be far more valuable for seeing the differences between different configurations, between this RAID 0, between a mirror and then the different RAID Z1, 2, and 3. And so we're going to run the rest of the tests in this mode. And just keep in mind, these numbers should be lower than what you would get if you had caching turned on and the normal synchronous mode. But also keep in mind that if you do a connection to the server over NFS, that by default is usually configured for synchronous. So you would get the synchronous performance. And oddly enough, I think if you do iSCSI, it defaults to async, which is a little strange. But it's good to understand that we're sort of looking now for the very low bar. So we're going to let this run, and we'll see what it looks like when it's completed. All right, so this has completed here. And first of all, let's look at the sequential read. And that is exactly what we'd expect, right around 2 gigabytes a second, which is the maximum read speed of the array itself. And so it's not the maximum speed of our network connection, which is slightly above that. So this really does represent the maximum speed we're getting from that SAS controller and those 4 SAS channels. So that's exactly what you'd expect with no caching turned on. The write speed, getting 1.2 gigabytes a second with the most number of threads here, is really a good indication of the maximum speed we're able to write to the drives across both that SAS interface and the SAS disk. So the write rate's a little slower than the read rate on those drives. And so that gives you a good idea of what happens as fast as we're going to go. So 1.2 gigabytes a second is pretty good for an array like this. And that'll give us a good metric to see how other configurations, either mirrored or RAID-Z configurations, compare. And then we're also going to look at this first line of the random. So 35 megabytes a second for the read, and it was 135 before, so quite a bit slower. Again, because of course the previous number was fundamentally all coming from cache. So this is really an indication of the array disk speed's ability to do random IO. And then the write 12 megabytes a second, same thing. That's in synchronous mode. Everything's going to be written to disk. And we don't have any log devices here. So this is a good indicator of sort of the lower bar of what the speed will look like. So this is for that spanning array. So let's go back over to our file server here. And let's take a look. We have another little script here to create a mirror version where the zpool is made up of sets of mirror disks. So 8 sets of 2 disk mirrors. And so let's run this real quick here and have it create the mirrors. And so this is a configuration that's going to be pretty common. It's where you have a bunch of disks and you put them in mirror groups. And so we're going to have 8 vdevs, each with 2 disks in the vdev that are mirrored. And it's a configuration a lot of people will run for high I/O performance is one of the things. And remember, we're going to do the ZFS. Let me just scroll up here. We're going to do that ZFS set and turn the cache off, and then also turn the sync on all the time. And so with that running, we're going to go back over here, and we are going to run all the tests again and see how it performs now when that array is a set of disk mirrors with 8 vdevs. Okay, this is completed, and look at that. So read performance sequential, very good, 2.1 gigabytes a second. So definitely right at the maximum read capacity of the array and of the SAS interface. So that's not to be surprised about. Write performance though, 718 megabytes a second. So 0.7 gig per second versus around 1.3 before. So it's about half, and that makes perfect sense because this is a mirrored array. So for every write transaction generated in this application, it's generating 2 to disks because it's got to do 1 to each mirror set. And so that performance number is really close to what you'd expect to get in a mirrored array. And that sort of indicates the potential write penalty performance of a mirrored setup, particularly in a case of a synchronous environment. So the random, this one with the first row of random here, so a score of 29, and so we had 35 before, so it's a little bit slower in read performance, and then the write performance is quite a bit slower. It's 9. It was 12 before, so it isn't actually as much of a drop in the write performance on random, probably because the overall speed limitation has to do more with the combination of random ops, that and being synchronous, meaning it has to go all the way down the stack and back up the stack across the network back to here. So that may be a bigger bottleneck. But it does give you an idea that, you know, the mirrored setup is quite good. The writes are a little slower, of course. Read performance, though, is fantastic. And even random read performance was very, very good. Again, it's about what you'd expect for a mirrored setup. And so we're going to go back over to our server here. And we have another script here for creating a RAIDZ1 configuration. And so this will take all the disks and create 2 vdevs. Each vdev has 8 disks running RAIDZ1. That means that you will lose 1 disk in each vdev for parity in terms of space. So we'll lose 2 disks of space across the entire array. So about 1/8 of the space of the array will be used for redundancy. Compared to the mirror, we're using half of it. So let's run this guy here. Create RAIDZ1. Let that run. And I think, you know, before we had, how much we had before? Put it down here. So with a mirror, yeah, with a mirror we had 100 terabytes of disk space, of course, so it's half. And so this is RAIDZ1, so 172 terabytes of disk space, which is about right. And so yeah, so we're gonna let this go back over to the Windows box here. We got it set up, yeah, 2 arrays or 2 vdevs. And so let's run this again and see how it performs running RAIDZ1 across 2 of the vdevs. Okay, this finished up. So the sequential read, very similar, but we'd expect, same thing, limited by the disk array read speed. The sequential write, though, 936, so a little bit faster than the mirrored, and that makes sense because in the mirrored array, every transaction generates 2 transactions. In this case, spanning across the disks, every transaction for 7 disks will generate 8 disks worth of transactions. So it's a little less total overall write bandwidth needed for RAIDZ1. So again, sequential performance, as you expect, is really, really good. And the random performance is where you'd expect it to be, which is noticeably different. So random read was 7, and so it was 29 before. So that's quite a bit slower. Again, there were 8 vdevs before. There's only 2 vdevs now. And so in this case, this test has 16 threads doing it. So it's not surprising that you'll get a lot of blocked I/O on only having 2 vdevs. And of course, on the right, you have 5.5, and it was at 9 before. So the write performance isn't actually hit as quite as much, probably because there is overall very similar write performance in terms of being able to commit. But with only vdevs, 2 vdevs, the number of parallel operations that are going to get blocked is a lot higher. So these numbers sort of do indicate what you'd expect to see, which is that with RAIDZ1, you're going to get a lot more disk space, but your random I/O performance is going to be worse. But your sequential is very, very similar, actually a little better in this case. And so for an array where you're not running VMs, where you're just storing and reading and writing files from for things like Plex, this would probably have actually higher performance than your mirrored array. And so next, let's go back over and let's take a look. Let's give it a test here. So I have a create RAIDZ2. This creates the same thing as before, but makes the arrays RAIDZ2. So 2 vdevs, RAIDZ2, so 2 disks of parity space effectively per vdev. So we're losing 4 disks total. So we're losing 25% of the total array space for redundancy. So let's give this a try. RAIDZ2. Okay. Let that run, let it create the array. And so I think that before we had cut down from, we were at 100 terabytes with mirroring, 172 with RAIDZ1. So RAIDZ2 is going to be somewhere in the 140s, 145 terabytes of disk space. Yep. And so now we have a RAIDZ2 array. We're going to go set 2 parameters to turn the caching off and synchronous always. And then we're going to go back over here and run another set of tests. So let that run and see how it performs. Okay, this finished up for the RAIDZ2 sequential read performance as expected. Fantastic. 2.2, actually the best so far. Totally limited by the read speed of the drives in the array. Write performance, 838. So a little slower than RAIDZ1, but faster than Mirror, which makes perfect sense because with RAIDZ1 or RAIDZ2, you're going to have a little more disk writes per IO block on average than with RAIDZ1 because there's a little more redundancy. So that number makes good sense. A little better performance than mirroring. And on the random, 7.93, so almost the same as with RAIDZ1. And the write performance, 566, it was 5.5 with the RAIDZ1. So again, RAIDZ2 and RAIDZ1, very, very, very similar performance. You generally would shy away from RAIDZ1 with disks this big. The rebuild time would be extremely long, and it would block a lot of performance of the array. And at that point, you're at pretty high risk. So this sort of shows that there's not a huge penalty for going to RAIDZ2 other than losing some disk space. And so let's pop back over and let's get another test started here. We have a create RAIDZ3, which will create 2 vdevs with RAIDZ3 in each of the vdevs. So using 3 disks for redundancy. And so this will eat up a little more RAIDZ3. Will eat up a little more disk space than we did with RAIDZ2. I think RAIDZ2 we ended up having 145 terabytes of usable space out of 200. And so we should be something in the 112, 113, 114 terabytes, 117 terabytes. There you go. So RAIDZ3 across each of the 2 vdevs. Let's give that a performance test. Let me go make sure I put on the synchronous always and disable the read cache. Okay, let's let this run and see how it performs. All right, this finished up doing the testing. So remember, this is RAIDZ3, and look at that. So reads 1.9, very, very similar to the rest of the configurations. Write 763, so it was 770 for mirror, so very close to mirrored performance. Not surprising, these are 8 disks in a VDEV, RAIDZ3, so for every 5 writes, you're doing 8 writes total, so relatively close in ratio. So I'm not surprised to see that number. So the RAIDZ3 performance is really similar to the mirrored performance on read and writes. Of course, in random IO, it's a lot slower. So 5.5 versus almost 8 for Z1 and Z2. So a little bit of a hit there for sure. The writes at 4.9 versus 5.5. So not a huge difference in write performance on random IO, but a little bit slower for sure. And so with RAIDZ3, you gain an extra bit of redundancy in the disks, and you do lose a little bit of performance overall. I think you can see that RAIDZ2 in some ways is kind of a sweet spot for the performance. But another thing we should try is let's go back over to the array and let's create an array. And I made a script for this, create RAIDZ2-3. And so this is going to create an array. We're using RAIDZ2, but instead of 2 vdevs, we're going to do 3 vdevs. So 3 vdevs, 5 disks in each vdev. Now that's 15 disks. So we're going to have 1 disk left over, which we're going to use as a spare. And so let's create this RAIDZ2-3. And this is going to go, so the RAIDZ2 was like 145 terabytes before. And so this will be down to like maybe 115, 113 terabytes, something like that. So it'll be slightly less, yeah, 113. So we had 117 with RAID Z3, but only 2 vdevs. So this is only a slight difference in total available space. RAID Z2s, and you have a hot spare that will come in on any one of the 3 vdevs if you lose one of the disks and it goes fully faulted. So let's give this a try. We're going to go set our parameters here for the cache and for synchronous. So again, a good worst case test. And let's let this run and see how it performs relative to having just 2 vdevs. Okay, our RAID Z2 with 3 vdevs has completed. You can see read speed sequential 2 gigs, no surprise there. Write speed 768, so that's really, really close to the mirrored performance and really close to the RAID Z3. It's not surprising compared to the RAID Z3 because this is 3 vdevs, but each vdev only has 5 disks, and so for every 3 disks of writing, you have 5 disks of writing total, so the ratio is just slightly worse there. So the numbers are about what you'd expect. Very similar performance, though, towards sequential write performance for RAID Z3. And the random performance, though, is where you see a good jump there. So 13 versus we were at, what, 8 before with RAID Z2, so with only 2 vdevs. So add an extra vdev, added about what you'd expect in random performance. The writes a little less. It was 5.6 before, and now it's 6. So that's somewhat similar. So random write performance didn't gain nearly as much as random read did. But overall, the performance of the array is better with the 3 vdevs than with 2 vdevs. And so in contrast to RAID Z3, it's nearly identical sequential performance, but better random performance, and not a huge difference in overall space available, 117 versus 113. So pretty similar. And so I think in general, one of the big lessons here is that, well, there's several lessons. The first one is that for sequential stuff, you're limited mostly by your network and your raw disk speeds. Fretting over whether or not you want to do mirrored RAID Z1, 2, or 3 is not a huge factor for that kind of simple sequential reading and writing of files. Your memory bandwidth may be, or your network bandwidth may be the biggest limiting factor. But within the idea of building an array like this, where it's really meant to be a kind of a big storage array, RAID Z2 is an excellent compromise of both having good resiliency. So you have 2 disks of parity effectively in every group. And depending on the number of disks you have, you can often have more vdevs with RAID Z2 than with RAID Z3. And so I think that in some ways, the RAID Z2 with 3 vdevs is an ideal sweet spot here. The only thing I'll caution on is that the spares are an interesting thing. They don't necessarily work just like you might think. I mean, they're useful in the sense that if you have a disk that fails, and it fails in the correct way, then ZFS will pull that failed disk out of the pool and bring in the hot spare, which will then immediately start resilvering so it can be a member of this new vdev group. And that can happen all automatically without you having any presence there. And so that's a good feeling because you're not down to just 1 disk of extra redundancy. You'll be back to 2 after the resilvering time. But it only does it in cases where the disks fail in particular ways. And there can be some, I've seen some faults before where there are read-write errors that start creeping up, and it won't fail over to the spare at that point. It'll only fail when it actually faults the array. And also, once it's faulted the array, there's some tricks in configuring it. You can't really just use that one forever. You have to pull it back out and replace the original disk first inside of the Z pool. Nothing magical or science, but it is an interesting thing in that it isn't as super easy as you might expect it to be. It isn't a bad idea in the case that you can't get to the array to have hot spares, because even if it doesn't automatically fault, you could certainly manually fault it to make it use the hot spares. And it does start the resilvering process faster. That's a good thing, because with a really big array with big disks, if you have 20 terabyte hard drives, those resilverings can take days and days to do, also while stopping or really slowing down performance of the array. And so this particular configuration is, I think, what we're going to stick with for now. It's a great one. One last thing is we did not add a cache drive or an slog drive. And those are very interesting things, especially for a high performance array. And so in our next video storage series, we're going to build not sort of a big long-term storage array, but a high-performance array for running VMs on. And we're going to do that both with pure SSDs and also with normal mechanical spinning hard drives. And in that environment, we'll be able to explore a little bit more about the effects of having a cache drive and an S-Log device, especially with significant number of synchronous writes. The S-Log device can come into play in that configuration. But for this one, though, we'll call this to be a pretty decent array. For read and write performance sequentially, it will work very well, and you have a good deal of storage and a good deal of reliability. And so we will end this video here, and stay tuned for the next video series on storage, where we're going to do some more high performance things.